And welcome to Electrical Grind. In the previous two lectures we have learned about SOP form of Boolean Algebra and POS form of Boolean Algebra expressions. Using those two reduction techniques we could solve or simplify the resultant Boolean functions. In this method, using graphical representation, we will try to simplify the Boolean expressions to obtain the real minimal expression. As we can see, in the POS and SOP forms, we had to follow various algebraic rules. But here, by using the tabular or graphical representation method, we could solve easily the Boolean expressions. Here we have two methods, the Kmap method or the Karnaugh Map method and the QM method, which is also known as Quine-Mikulski method. In this video we will learn about the Kmap implementation. So as we can see here, for n variable we will draw a Kmap having 2 to the power n number of cells. As we could see, for say 3 variables, we will obtain 2 to the power 3 equals to 8 combinations. So in this way, for the Kmap representation, we will use similarly the table representation, truth table representation, and implement it in the map format. For that, we will put one variable along the first column and the other variables along the row columns. So here, as we can see, I have taken x as the column, x variable as the column, and yz variable as the row. So here we can see the first value that we have inserted will be 0 0, and after that we will only change every value by a single bit. This is also called gray code encoding. So what will be the benefit of this? This helps us to obtain a cyclic order. Hence we will be able to obtain after 1 0 again back to 0 0. And as such, for the same combinations as per the truth table, we will place the decimal equivalent in the boxes. So for all zeros we will have 0 decimal value, and similarly, let's say for this column and this row, as we will obtain xyz's value equals to 111, which is the decimal equivalent of 7, and hence this cell will be the decimal equivalent of 7. And as per that, like previously, as we have seen in SOP and POS forms, the value with logic 0 will have the represented in the complement form, and the value with logic 1 will have the variable or literal in the uncomplemented form. Now let us understand the rules to simplify Kmaps. So we will be using groups of order 2 to the power n. Minimum grouping will be of 2 cells, and maximum will depend upon the number of variables that we are given. So for example, if we have a 4 variable Kmap, then the highest number of possible groups of ones we can form is 8, 16, including 2, 4. So as such, we will form our groups. Now there should be a slight confusion as to how many literals will be present in the output. As we can see here, if there is 2 variables, the maximum number of possible groups of ones, that is applicable is for 4. So let us see how it is. If we have a 2 variable Kmap, we will generate 4 cells. So the maximum possible combination will be of the 4 cells, but this will yield 0 literals because every literal will be of different values, hence it will not generate a single output. Hence the output will have no literals present, hence it is written as 0 for the maximum possible group. Now let us see its application with the following examples. So first we will explain a 2 variable Kmap. So here, as we can see, we are being given the min terms 0, 1 and 3. So we will accordingly put logic 1 in these cells. So 0, 1, 2 and 3. Here we will put the logic 1 as per given in the question, and then we will form the groups. So the minimum possible group we could form was of individual, but if there is a adjacent cell where we can form groups, as we have seen in the rules column, so we will use the maximum possible group. So here maximum possible group is of 2, so this will become our first group, which will result in A bar actually, and this will result in B. So here is a slight mistake, it should be A bar plus B. Similarly, for the 3 variable Kmap, say it is given in the question as min terms of 0, 2, 3, 4, 5 and 6. So we will put the decimal equivalents here, and as we can see, we will put the values 1 against all those given decimal equivalents. After that, we will try to follow the maximum possible groups. So here we will get 1 possible group, here we will get 1 possible group. Now as I have shown you that we are taking this group as well as this group, but you may have a slight confusion because you are thinking that this is the adjacent cell to this first cell. But as I have said previously at the beginning of the slide, that gray codes are cyclic in nature, so after 1 0 the cycle repeats to 0 0. So in a way this cell's equivalent is 1, and also this cell, sorry, it is 2, so 0's equivalent is actually 2 and 1. Similarly for this cell where 1, its adjacent cells are 0 and 3. So by that cyclic rotation, our Kmap is also cyclic in nature, and hence we are able to form the maximum group of 4, which ultimately becomes as such, and we are able to generate this expression, minimal expression. Let us understand with 4 variables. So as per the question given, we will now insert the values and we will try to obtain the maximum possible groups. So this is a group that we can see of 4s, then this is a group of 4s, then this is a group of 2, this is a group of 2, and this is single out. Now there might be a confusion as to why we are forming here a single group and here we are not forming a single group. Again, as we can see here in the rules column, that we will always try to use the maximum possible groups. So here, as there are no adjacent cells with 1 value here, we are unable to form any groups. But for this value, there is an adjacent cell at the corners, so we will take its group. Similarly, for the next question, please try to solve it as I have shown in here. You will get the desired result. Now let us understand what is prime implicant and essential prime implicant. So implicants are all the product terms that are being covered by either one cell or multiple groups. So this can also be a this can also be an implicant, this is also an implicant, this is also an implicant. Now the question is, what is prime implicant? So prime implicants are those without whose groupings the K-map will further not give us the required or desired minimal expression. So it is the product terms which covers the maximum possible number of adjacent min terms. Okay, as we can see here, this is the major group which covers the most of the min terms. There might be a question as to why we did not consider this, because it was a group of 2's. Now some might also say that why did we not take this group as a group of 4 and obtain the K-map solution. But there is a restriction that says that we have to either take a rectangular or a square form so as to adjust all the min terms. If we take such a combination where we are not getting the desired shape of a square, say we are getting a shape of T or sometimes plus or different other shapes, then such combinations are known as non-prime implicants. So these are min terms which actually do not form the bigger part of the square. Here, even though as we can see we have 8 squares, we are not possibly trying to attain the minimum expression through them. Now let's see what is essential prime implicants. Essential prime implicants are those prime implicants which contains at least one min term that cannot be covered by any other prime implicant. So hence we can see here that this is also a essential prime implicant, because here we have a term which is not being covered by anyone else. Similarly, this will also result in a essential prime implicant. So both of these are prime implicants, because here this one has not been covered by this bigger group. Now we will see what is redundant prime implicant and selective prime implicant. Redundant prime implicant. Suppose we have a group of min terms which have already been covered by one or more than one essential prime implicants. Now if we again try to reconsider these min terms for the K-map solution, we will just end up with getting a redundant value which will ultimately may be solved by Boolean algebraic reduction formulas. So such prime implicants which have already been covered by either one or more than one essential prime implicants are known as redundant prime implicants. So what is selective prime implicant? The prime implicants which are neither essential nor redundant are known as selective prime implicants. As we can see here, this group is not essential because the essential prime implicants have already been covered, but this one can be combined either with this one or can be combined with all these other 3 ones to form a minimal solution. So in such a case, if there arises a min term which can form either a smaller square or a bigger square, such prime implicants are known as selective prime implicants, or in other words, these are also called as non-essential prime implicants. They may appear in the minimal expression sometimes and may not appear as well. Suppose, as we can see here, it will using selective prime implicants, we always end up with multiple minimal expressions. So if we consider this with the grouping of 2, we will end up with A bar C D. And if we consider a group of 4, then we will end up with A bar C. Okay, this should be A bar C D bar. Now let us understand the don't care combinations in a Kmap. So sometimes we obtain input combinations which do not affect the output expressions. Such input combinations are not specified and hence are not affecting the output. So these such input combinations which are invalid or do not influence the output are known as don't care combinations or don't care values, and they are denoted either with a D or with a X or with phi symbols. Now, what is their use in the reduction process? By any means, by themselves, they do not have any particular values because they are neither logic 1 nor logic 0 by themselves. But if we have, say, 3 minterms in a Kmap along with a don't care input combination which is able to reduce the group by forming a bigger square, then such don't care conditions during reduction process will be treated as logic 1. But as we can see here, we have two don't cares at position 2 and position 4. The don't care at position 2 is however not considered for the reduction process here because this will only result in a new value which will not help us obtain the reduced expression, because if we consider this don't care with the 1 to form a group of 2, we will end up with A bar C D bar, which is not helping us in the reduction process as because this by itself has no value. But here this don't care we have used it to consider, because if we did not consider it, we would have ended up with two groups of ones, one here and one here, and then one here. Then again we would have obtained three variable combinations at the output, but it wouldn't have been reduced because as we can see from the previous rules table that if in a 3 variable or a 4 variable Kmap we will use the combination of 2, it will lead us to 2 literals in the output, and for 4 variable it will be 3 literals in the output. But here we have, as we have considered the 4 literals, we only ended up with 2 combinations. Okay, so with this we are ending our basic understandings of a Kmap, and for a bonus session we will see how we are implementing 5 variable and 6 variable Kmap. In this video I will not be covering this 5 variable and 6 variable Kmap. However, let us just go through how a 5 variable Kmap is formed. So for a 5 variable Kmap we will have 32 variables combinations, hence 32 cells. So how will we use? We will use 2 4 variable Kmaps. 2 4 variable Kmaps, and we will term one with the first literal as logic low and the second literal as logic high or logic 1. And then accordingly we will place the numbers. So when groupings a 5 variable Kmap, we will have to assume that this Kmap is exactly under the next one's is, and hence the adjacent of 0 is not only 2 now, but also 0's adjacent will be 2, 8, on the upper side will be 16 as well, and similarly for say 31 position it will be lying exactly above 15 and its adjacents. Okay, so we will get a much more complex result. Hence, for such results for higher variables, we do not prefer using Kmap because it will be generating more complex values and it is difficult to do chart wise itself. So this is one of the major drawbacks of Kmaps, that it is limited up to 4 to 5 variables. With this lecture we will end it here, and in the next lectures we'll understand tabular methods as well as how to obtain combinational circuits and sequential circuits. Thank you.